next family is probably the most obscure of all of the elements, the rare earth metals. They are elemental oddities. They are the black sheep of the periodic table family. Black sheep is actually quite fitting, since many were originally discovered from this black ore called gadolinite, and they are currently mined from this blackish ore called monazite. The rare earth metals frustrated and mystified the early chemists. All 15 are very, very similar, and extracting them was a 100-year-long, frustrating and tedious process. Early on in the process, William Crookes said, "The rare earth elements perplex us in our researches, baffle us in our speculations, and haunt us in our very dreams. They stretch like an unknown sea before us, mocking, mystifying, and murmuring strange revelations and possibilities." To save space, nearly every periodic table you see moves the rare earth metals down to the bottom, like a footnote to the periodic table. The rare earth elements, also known as the REEs, were thought to be rare when first mined. They are not. In fact, cerium, lanthanum, and neodymium are more abundant than lead, or gold, or silver. The real problem is that they are not concentrated in big enough quantities to be easily mined. And the reason they are so similar is once again based on modern atomic theory. Rare earth elements don't add electrons to their outer shell, which would make their differences more noticeable, like we see in the main group elements. Instead, their electrons are added deep into the third to last shell. Thus, the outward differences between them is very subtle and makes them difficult to separate. They are also called the lanthanoid metals because the element lanthanum heads this reclusive group. Just a few years ago, these elements were mere scientific curiosities, fairly useless actually. They weren't rare in the earth, they were just rarely used for anything at all. But from their relative obscurity, future technologies have made them almost indispensable, especially in the strong magnets they can produce. In fact, without these shy elements, our high-tech environment would probably grind to a halt. Incredibly powerful and small rare earth magnets are perfect to drive the tiny speakers in the earphones in your iPods and cell phones. Every computer hard drive uses powerful rare earth magnets for the motor and actuator arms. Small motors use rare earth magnets to spin the rotors, including the spinning barcode scanner at the grocery store. There are no known substitutes for these magnets. Every hybrid car uses about 50 pounds of rare earth metals in the electric motor magnets and the regenerative brake system that captures released energy when braking. In every flat screen monitor and every flat screen television, rare earth europium with yttrium makes the red color and terbium makes the green color. There are currently no known substitutes to make these colors in these monitors. In certain wind turbine applications, 2 tons of rare earth magnets are required in the permanent magnet generator that goes on top of the turbine. No rare earth elements, no turbines. It is estimated that nearly 25% of all new technologies use rare earth elements, and the demand is increasing. Currently, nearly 100% of all rare earth element output comes from and is controlled by China, and all from this one mine. Here in Inner Mongolia, this new demand has strained supply, and there is growing concern that the world may soon face a shortage of rare earth elements. In spite of all this, the rare earth elements still remain obscure and fairly unnoticed by the general population. It seems to be their destiny. Lanthanum. Lanthanum is Greek, meaning I am hidden, which pretty well sums up all of the rare earth metals. All of the rare earth metals can be found in this blackish ore called monazite. Cerium, named after the asteroid Ceres, discovered around the same time, which, it turns out, is much more like a very small planet than an asteroid. Cerium is the most abundant rare earth metal. Praseodymium. Compounds of praseodymium were similar to lanthanum, of course, but with a greenish tint. Thus, praseodymium means green twin. Neodymium. Neodymium was discovered as a result of separating out praseodymium and was named the new twin. Neodymium magnets are incredibly strong. Two small neodymium magnets can snap together with such force that it will easily pinch skin or break bones. But they are the strongest and least expensive rare earth magnets. Promethium, the only radioactive rare earth element and the last one to be discovered. In Greek mythology, Prometheus gives fire to mortals by stealing it from the gods. The discovery was so difficult the scientists felt like they too were virtually stealing it from nature. Samarium, named after a virtually unknown person, the chief of staff of the Russian Corps of Mining Engineers, Vasily Samarsky-Baikovets. It was the first element named after a person. Samarium mixed with cobalt also makes strong but very expensive magnets. Those are the first 6 rare earth elements, and the most useful so far. The remaining 9 rare earth elements have very few applications, but we will list the main use of the metal even if it's not very common. These rare earth elements are very difficult to find, thus expensive, and so far their cash value is very limited. There's a lot of potential, but their real value probably remains sometime in the future. Europium. Europium was named by the French chemist who discovered it after the continent of Europe. You can thank europium for the brilliant red colors in your monitor and television screen. Gadolinium. Named after another fairly unknown person, the Finnish geologist Johann Gadolin, who discovered the very first rare earth element. Gadolinium is given to patients to highlight tumors when seen with X-rays. Terbium, the second element named after that famous little mine in Ytterby, Sweden, where it was discovered, used as the green phosphorus in television screens. Dysprosium. Dysprosium is another rare earth so difficult to separate out that its discoverer named it hard to find in Greek, dysprosium. There are very few applications for this element. Holmium, Latin for Stockholm, the hometown of its discoverer. Until recently, there were no practical uses for holmium. Now, some lasers and rare earth magnets use this element. Erbium, the third element named after that famous little mine in Ytterby, Sweden, where it was discovered, another rarely used element. Thulium, named after the mythological island of Thule, the northernmost island of the world. Thulium's discoverer believed Thule Island was an ancient name for his homeland of Scandinavia, and in this way he named his element after his homeland. Thulium has very few known applications. Ytterbium, the fourth element named after that famous little mine in Ytterby, Sweden, where it was discovered. It has no major commercial uses. Lutetium. Lutetium from Lutetia, the Latin name for the city of Paris. Lutetium is generally the most expensive natural element today and often sells for around $6,000 an ounce. It is extremely rare since nobody produces it because nobody uses much of it. For people who collect samples of the periodic table of the elements, lutetium is usually the last one they ever get, if they ever get it at all. Yttrium, erbium, terbium, ytterbium. The reason you find some of these names confusing is because they are confusing and obscure. The black sheep of the periodic table families. Some toys you can only build so big before the structure itself can't hold it together and it begins to fall apart. In a similar way, all the elements after bismuth become so large that it can't hold it together and they begin to fall apart. They become radioactive. Regarding radioactivity, every element on the periodic table has at least one isotope version that is radioactive. Plus, technetium and promethium are exclusively radioactive. Then, every element after lead and bismuth are radioactive and are called the heavy radioactive elements. These can easily be divided into two groups: natural and artificial. By natural, we mean elements that can be found in significant quantities naturally in the Earth. The first 92 elements, from hydrogen to uranium, are generally recognized as the natural elements. The four exceptions are, again, technetium and promethium, and astatine and francium. Four natural elements that are virtually non-existent in the whole universe, except for a few atoms here and there. By artificial, we mean that elements after 92, uranium, exist only as man-made creations and are not found in nature, with two minimal exceptions. Neptunium and plutonium are technically found in nature, but only in very, very tiny trace amounts. Some of these elements are quite useful in industry. Others existed only as a single atom in a laboratory experiment and then disappeared forever. Polonium. Polonium was named by Marie Curie for her homeland of Poland. Polonium is one of the deadliest substances known. If ingested, polonium is at least 1 billion times more toxic than cyanide. It is so strongly radioactive, it causes the air around it to glow blue. Polonium was used as the trigger in the first nuclear bomb test. Today, polonium has almost no industrial uses. Astatine, an incredibly unstable and rare element. There is an estimated 1 teaspoon of astatine in the entire Earth's crust. Astatine is Greek for unstable. Radon, named after Marie Curie's radium. Radon is a radioactive gas, technically a noble gas, as it is in the noble gas column, and is inert and unreactive like the other noble gases. Radon is produced through the natural decay of uranium ores, where it has a half-life of about 3 days before decaying into other elements. Radon gas is 9 times heavier than air. In fact, it is the most dense gas on the periodic table. In poorly ventilated mine shafts, the gas posed a cancer risk as miners inhaled the odorless, tasteless radioactive gas. The risk for radon gas exposure in residential areas is still highly debated. Francium. Francium, named for France where it was discovered. So short-lived that no weighable quantity of francium has ever been prepared or isolated. Gallium was also named for this country, France. Radium. Radium is Latin for the word ray, named by the discoverer Marie Curie, who was awarded the Nobel Prize in Chemistry for her work. The worldwide production of radium is now at about 2 pounds per year. That's it. Radium is the Greek word for ray, and actinium is named for the Latin word for ray. A nasty, unstable element, quite possibly the most dangerous element on the periodic table. Due to its intense radioactivity, actinium glows in the dark with a pale blue light. Thorium, named after Thor, the Scandinavian god of thunder, though nobody really knows why. We encounter thorium as a component in many gas-light mantles. The cloth, or silk fabric, is saturated with the metal thorium. When the little net bag is placed in the flame the first time, the fabric burns away, leaving the metal behind, which burns brightly. The mantle shrinks and is now very fragile. The amount of radiation in the mantles is very small and virtually undetectable, especially behind the glass, though you probably don't want to carry mantles around in your pocket for weeks, and eating them is highly discouraged. Protactinium. Protactinium meaning first ray. Proto-actinium, since it first decays into actinium. To get just 5 ounces of protactinium, you need to process over 60 tons of radioactive waste. There are currently no uses for this element outside of scientific research. Uranium, named for the planet Uranus, which was discovered 8 years earlier. Uranium is the last stop for naturally occurring elements, number 92. After uranium, all elements are man-made in laboratories and are called transuranium elements, meaning after uranium. Only 1% of uranium ores contain the famous isotope uranium-235, and that's the one you need to run nuclear power plants and make nuclear weapons. Depleted uranium is very heavy, as you can imagine, and it is used to make very dense armor-penetrating projectiles. Neptunium, named, obviously, after the planet Neptune. Neptunium is used only in research laboratories. Plutonium. Plutonium was named after a famous cartoon dog. No, just kidding. This was the third element in a row named after a planet, but in this case, Pluto is now called a dwarf planet. Like uranium, plutonium is used for nuclear power and atomic weapons. The first nuclear test and the second bomb dropped on Japan both had cores of plutonium-239. Plutonium generators help power space probes and other space instruments. If you had a golf ball of plutonium in your hand, you would need several layers of lead-lined gloves just for protection. The ball would be incredibly dense and hard, and cutting it with a saw would be virtually impossible. It weighs over 2 pounds and would be very hot in your hand just from the sheer amount of radiation decaying out of the material. According to the World Nuclear Association, plutonium is toxic because it is so highly radioactive, but chemically, aside from the radioactivity, plutonium is about as toxic as caffeine. Americium. Americium is named for America, where it was created, just as europium was named for Europe. Some pronounce it americium. The most common use is in smoke alarms in your house. Inside a smoke alarm is a circuit board where the electronics are. Mounted to the circuit board is the horn that sounds the alarm. The sensing chamber is where air and smoke enters, and the battery powers the device. Inside the sensing chamber is this aluminum casing with a little star-shaped button of americium in the middle, decaying away and throwing off alpha particles, ionizing the air. The alpha particles are indeed toxic, but due to their large mass, they are easily stopped by a sheet of paper, and they are certainly stopped by all the metal and plastics surrounding your home smoke detector. The battery's positive and negative terminals are attached through the circuit board to these two metal plates. The americium-241 naturally emits alpha particles like bullets, knocking electrons off the atoms in the air between the plates. The result is ionized air, with lots of positive cations and negative electrons. Like a magnet, the positive cations are naturally attracted to the negative plate, and the negative electrons are attracted to the positive plate, making an electric current through the air and completing the circuit. Now, as long as the current flows in the air, the circuit board keeps the alarm shut off. But when smoke enters, it physically blocks the alpha particles streaming from the americium. With no more ionized air, the path is broken, and the circuit board instantly diverts electricity to the horn, and the alarm sounds. Thorium in mantles and americium in smoke detectors are the only radioactive elements you can buy in your grocery store. Curium, named in honor of Marie and Pierre Curie. Like plutonium, curium decays rapidly and thus generates a lot of heat. Now, normal satellites use solar panels to generate their needed electricity. But for space probes that travel far from the sun, solar panels don't work well, and curium is often placed in a device called a radioisotope thermoelectric generator. The intense heat from curium's radioactive decay is used to generate the necessary onboard electricity. Berkelium, named for the University of California at Berkeley, where it was created. Like several of the other transuranium elements, the use of berkelium remains a mystery, like a treasure waiting to be unlocked in the future. Californium, again named for the University of California at Berkeley, used in chemotherapy and a few specialized applications in industry. In 40 years, less than 10 grams of californium have been produced. The cost of californium is about $10 million per gram, plus shipping and handling. Einsteinium. The most famous scientist of all time, Albert Einstein, probably deserves to have an element named after him. Unfortunately, this element decays away completely in a few months and is probably poisonous and has no known applications. Fermium. In honor of Enrico Fermi, who developed the first nuclear reactor and quantum theory. Making fermium is pretty futile. No sooner does an atom form in a nuclear reactor than it disappears. There are no known applications since there is no piece of fermium to experiment with. From here on out, all of these elements are known as transfermium elements, beyond fermium. This is the twilight zone of the elements. To our knowledge, none of these elements exist in the universe today, certainly not on Earth, and only a few atoms of each of these elements ever existed in nuclear accelerators before decaying away into atomic debris. None of the transfermium elements has any known biological, human, environmental, or economic role, other than the fact that they are really, really expensive to make. There is a constant race to be the first to make the next element and to name it, mostly between the university at Berkeley and the nuclear research facility at Dubna, Russia. The rivalry between the labs can get fierce and seem pretty absurd to outsiders, but you have to cut the chemists and the physicists a little slack on this, because after all, a new element doesn't come around every day, so adding one receives a lot of attention and lively debate. Mendelevium. Mendelevium, named for Dmitri Mendeleev, the father of the periodic table. The original batch of 17 atoms managed to stay around for all of 78 minutes before breaking down into simpler elements. Nobelium, named for Alfred Nobel, the Swedish chemist and founder of the Nobel Prizes. Curium, with a proton weight of 96 protons, was bombarded by carbon with a proton weight of 6. 96 plus 6 is a proton weight of 102 protons. Nobelium. Lawrencium, named for Ernest Lawrence, the inventor of the atom smasher, or cyclotron, which produced all of these transfermium elements. This is the final element that lasted longer than 1 hour. From here, the elements get pretty sketchy and the names are fiercely contested over. Rutherfordium. In 1960, an element naming war broke out between two laboratories starting with this element, number 104, and it took nearly 37 years to resolve it. Both Berkeley and Dubna claimed priority in creating the element and suggested their own names. Finally, in 1997, after a lot of heated talk and a little horse trading, at the 39th IUPAC General Assembly in Geneva, Switzerland, it was agreed that element 104 is Rutherfordium, named after Ernest Rutherford, and element 105 is Dubnium, named for the research facility in Russia. Element 106 is Seaborgium, named for the amazing Glenn Seaborg, who was the creator or co-creator of an incredible 10 of the periodic elements: plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and this element, which was named in his honor while he was still alive, yet another flaming controversy. Seaborg was a Nobel laureate, the author of more than 50 books and 500 journal articles. He was given over 50 honorary doctorates and received so many awards and honors, he was once listed in the Guinness Book of World Records as the person with the longest entry in Who's Who in America. Element 107 is bohrium, named for Niels Bohr, the Danish physicist who developed the modern theory of atomic structure. Element 108 is hassium. Now a third laboratory for creating elements steps in. It is the Institute for Heavy Ion Research, and is first in creating this element and names it after the Latin word for the state in Germany where the research center is located: hassium. Element 109 is meitnerium, named in honor of Lise Meitner. Lise Meitner was part of the team that discovered nuclear fission, an achievement for which her colleague Otto Hahn was awarded the Nobel Prize, but without Meitner. Meitner is often mentioned as one of the most glaring examples of scientific achievement overlooked by the Nobel Committee. A later study concluded that Meitner's omission from the prize was, quote, a rare instance in which personal negative opinions led to the exclusion of a deserving scientist, unquote. But Lise Meitner gets the last laugh, having her own element, an honor that will last far longer than receiving a Nobel medal. Element 110 is Darmstadtium. Once again, the German Institute for Heavy Ion Research beats the competition and names this element after their city, Darmstadt, Germany. Element 111 is Röntgenium, named in honor of Wilhelm Conrad Röntgen, who produced and detected X-rays. Element number 112 is Copernicium. The team in Germany created 112 and chose Copernicium after Nicholas Copernicus, the astronomer. And yes, naming this after an astronomer and not a chemist caused a minor controversy, but it was a refreshing break from the long list of chemist names before it. As of the production of this film, elements after 113 have no names, and IUPAC assigns a temporary name until the creation of the element has been confirmed. And as we've seen, this can sometimes be a long, drawn-out, and political process. The temporary name is based on the element's atomic number. 0 is nil, 1 is un, 2 is bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct, and 9 n. Thus, element 113 is untrium. Probably not the most melodic sounding word, but it gets the job done. Element 114 is unquadium, and the Dubna, Russia lab team has this one in the bag. Element 115 is unpentium, and the joint venture between the Russians and the Americans seem to have a solid hold on their claim for creating unpentium back in 2004. Element 116 is unhexium. The Russian lab has claim to 116 for creating several atoms of unhexium in 2005. Element 117 is unseptium. The joint venture between the Russians and the Americans has an early start on 117, but Germany is moving in, trying to capture an unconfirmed sighting of unseptium. And the final element to date, though not yet officially confirmed, is element 118, unoctium. Only 3 atoms of element 118 have been detected in a race between Berkeley and Russia for primacy. Now, before we move on to the future of chemistry, just what do chemists do with the periodic table of the elements? Well, there are many ways in which the table is useful, and here are a couple of them. By sorting all the elements by their various properties, the elements with similarities and slight differences tend to group together, as we've seen, just like our periodic table of the crayons. Say, for example, that you found that iridium is a good metal for your pen nib manufacturing company. Hard, durable, not very reactive, good stuff. A little spendy, and prices are going up. So now what? Well, without the periodic table, you'd have to start guessing, trying maybe this metal or that metal, or giving up altogether. But you have the periodic table, and neighboring elements often have very similar characteristics. So you go to your periodic table and take a look. Let's see, what is like iridium but different? Hey, osmium is similar. And the cost of osmium on this particular year is less than iridium. Let's try some osmium and see how it works. Or another example, lead was used for years and years as cosmetics and in medicines, but as the toxicity of lead became found out, a substitute was looked for. What's next to lead that acts like lead and is similar? How about bismuth? And now, bismuth compounds are used to replace many applications previously used by lead, including cosmetics, plumbing applications, ceramics, and glazing. Why? All because the periodic table laid it out and made some of these decisions easier to make. Or another example, glass manufacturers commonly add sodium to glass, but we're looking for a way to make glass tougher, especially for use in television screens. They turned to the periodic table and tried one of sodium's neighbors, potassium. And sure enough, the potassium blend yielded a tougher glass for television screens, all because they had access to the periodic table. Another use is by applying your knowledge of the noble gas rule. Like, ferocious alkali metals want to bond with nonmetals to make the stable 8 electrons. You can mix and match how these elements come together to make new compounds, all because you know they are trying to fill their outer shell with 8 electrons. In short, the periodic table gives a level of predictability to the chemist. By knowing the main properties of each group and how they will react, industries can predict the properties of various combinations with reasonable confidence. They will know that cesium is in group 1 and thus will be a soft metal that will probably react even more violently than the element above it. Or, if they care messing with garlic breath tellurium over here in column 16 with 6 outer electrons, it will probably combine with 2 hydrogen atoms, making hydrogen telluride, H2Te. Why? Because that's how the other elements in column 16 combine with hydrogen. Oxygen makes water, H2O. Sulfur makes hydrogen sulfide, H2S. And selenium makes hydrogen selenide, H2Se. Also, it has not escaped the notice of the chemists that the even-numbered elements, 22, 46, 76, are all more stable and more abundant than the odd-numbered elements next door to them. Scientists have also noticed similarities in elements with the so-called Knight's move, 1 down and 2 over. Now, they aren't in the same group, but they have amazingly similar properties, like zinc and tin. Both alloy to copper to form brass and bronze. Both are fairly non-toxic, and both can form alloys with iron to prevent rust. Likewise, scientists have known for years about triads. The weight of this element and the weight of this element, when averaged, amazingly equal the weight of the element in between them. And there are many such mysterious triads in the periodic table. All this information suggests that there is something more fundamental or essential to the periodic table than we have yet to discover. These observations may get put to good use someday, and the ability to know this exists only because we have a systematic layout of every element, the periodic table of the elements. This kind of information is terrifically useful for industries in making decisions about where to spend their money and how to focus their research dollars. And just where industries are focusing their research dollars today will be the topic of our next and final segment of Chemistry 101, the future of chemistry.